Today we're going to talk about exponential functions. The general form of an exponential function is b to the power x, where b is a constant number, x is the variable, and we normally assume that b is greater than 0 and not equal to 1, because if b is a negative number, then certain power right complex number. For example, if I ask you what is negative 2 to the power 2, this is well defined, but if I write negative 2 to the power 1/2, then this causes square root of negative 2, which is a complex number. So to avoid these, bases of the exponential functions are picked to be positive. And if you pick the base to be 1, then 1 to any power is 1. So we normally do not pick the base to be 1. So all positive numbers, their base is not equal to 1. That's an exponential function. A simple example would be f of x equal to 2 to the power x. This is an exponential function, base 2. And how does it behave? You can find certain x values and y values to see how this graph looks like. xy, if I pick x to be, let's say, negative 1, 0, 1, 2, 4 points. 2 to the power negative 1, that is 1 divided by 2 to the power 1, which is 1/2. 2 to the power 0 would be 1. Anything to the power 0, by the way, b to the power 0 is always 1, as long as b is non-zero. So this is something we already know. And 2 to the power 1 would be 2. 2 to the power 2, 4. So we have certain points with their y values. We can draw those points. We draw it here. Okay, so let's say negative 1 here. We'll have 1/2. Here's 1/2. At 0, we have 1. At 1, we have 2, y value of 2. And at 2, we have y value of 4, somewhere up here. And if you pick, or maybe I should have picked another number as well. Let's say if I pick negative 2, what happens is you get 2 to the power negative 2. That is 1 divided by 2 to the power 2, which is 1/4. So at negative 2, y value is 1/4, somewhere here. And what you would notice is that the curve that goes through all these points would kind of look like this. And it never touches the x-axis. It approaches the x-axis, but it never touches the x-axis. Whatever you pick as the exponent for x, always the outcomes, all these outcomes, are positive numbers. What we see is 1/2, 1, 2, 4, 1/4. All these are positive numbers. So I can tell you that the graph of exponential function b to the power x is always above the x-axis. It never goes below the function. So what we can say is the domain of the exponential function means what inputs can you pick for the exponent is all real numbers from negative infinity to positive infinity. I can pick any x number that I want and replace it as an exponent. But what do we get as the range? The y values is all the y values are greater than 0. You never get to the x-axis, neither you will go below the x-axis. So the y values are always above 0. So the range is from 0 to infinity. So if the exponential function has the form of b to the power x, then the domain and the range are given through these two intervals. One is all real numbers, the domain, the range is all positive y values. So this is one example. Another example of exponential function would be something like f of x equal 1/2 to the power x, or 1/3 to the power x. So what you notice for this function is I can rewrite it as 2 to the power, or let me write it as 2 to the power negative 1. This is the same as 2 to the power 1/2 is the same as 2 to the power negative 1, and to the power x. And one of the properties is this is the same as 2 to the power negative x. You can write it this way. And if you remember, the relation between f of x and f of negative x is that if you change x to negative x, that's a kind of transformation that we learned from graphing, and this is a reflection about the y-axis. If you change x to negative x, the graph will reflect about the y-axis. So what it means is, if I graph this function 2 to the negative x, I just need to reflect the graph of 2 to the power x about the y-axis, and what you get is basically this curve. This green curve, if it's a reflection, assume this is symmetric. This is 2 to the negative x. This one is 2 to the power x. That's the relation between these two. But 2 to the negative x is the same as 1/2 to the power x. So kind of we can see that if the base, this is the base of the exponential. If the base is a number between 0 and 1, what you get is a decreasing function. You will get this green curve, which is the decreasing function. On the other side, if the base is greater than 1, like 2 to the power x, the curve will have this structure of increasing function. So we can say, okay, if I'm graphing the function f of x as b to the power x, depending on the base, if the base is greater than 1, like 2 to the power x, this is how the graph would look like. It would be increasing. On the other side, if the base is less than 1, but still positive, between 0 and 1, then it would be just a reflection of one of these cases, like 2 to the power x or 3 to the power x. It would be decreasing toward the x-axis. And one information that you can get through the graph is, if this is the case for the base, what you notice about the limit infinities, x approaching to infinity of the function, is if x is approaching to positive infinity, y value is approaching to y infinity. On the other side is if x approaches to negative infinity, the y value along this curve is approaching to 0. Similarly, for the other one would be if x is approaching to infinity, y value approaches to 0. And if x approaches to negative infinity, then the y value is approaching to infinity. This is the relation between the limits at the infinities, which you can write it as this. If you have the base to be greater than 1, what we know about the behavior of the function? If you calculate the limit at infinity, that's basically the behavior of the function. The function is increasing, as x increases, the y value, which is this is the y value. The y value increases toward infinity. On the other side, if you let the x to be smaller, x is going this direction, what happens to the y value is the y value is approaching 0. This is when the base is greater than 1. That means you had an increasing function. And the other direction, the base is between 0 and 1, everything would be flipped. So if x is increasing, y value is approaching 0. If x is decreasing, if x is approaching negative infinity, then the y value is going toward positive. And there are some properties of the exponential, but this is just a simple information that you already know about the polynomials. It's extended here, x squared times x cubed. You write it as x to the power 2 plus 3. Same is for the bases. If you have b to the power x plus y, you can write it as multiplication. If it's multiplication, you can write it as addition of the exponent, these two. If it's subtraction, you can write it as division. If a division is given, you can write it as subtraction. But the bases must be equal. And if you have x to the power 2 to the power 5, you say this is x to the power 10. The same, if you have 2 to the power x to the power y, this would be 2 to the power x times y. You multiply the exponent. That's b to the power x times y. And if you have if you have x times y squared, you would say this is x squared y squared. The same thing here. For this exponential function, the same properties hold. So these are nothing new. This is just a reminder of those properties that we have for polynomial. The same holds for the exponential. So here, use the idea that we had for the increasing and decreasing and find the following limit. what is the limit of 2 to the power negative x minus 1 as x approaches to infinity? If we replace infinity in here, what we get is 2 to the power negative infinity minus 1. Think about 2 to the power negative infinity. If we had 2 to the power x, this would have been the curve 2 to the power x. 2 to the power negative infinity, that means let x approaches to negative infinity. You're replacing negative infinity for x. What is the behavior of the function? The function at y value approaches to 0. So basically this means you have 0 minus 1 is negative 1. Or you can go look at the limit and rewrite this as 1/2 to the power x, because that's the same as 2 to the power negative x. And since, say, the base is between 1 and 0, then the limit of that would be 0 as x approaches to infinity. The other type of question that I ask you sometimes is, what if the limit of 3 to the power x divided by 3x minus 2? What would you do in this case? If you replace infinity, what you get is infinity 3 to the infinity divided by 3 to the infinity minus 2, which would be infinity over infinity. This is not possible to simplify. You cannot cancel out this and say 1. That's not true. So what you can do is use the idea that we had earlier on. Divide the numerator and denominator by the largest term. In this case, the largest term is 3 to the x. So I'm going to divide everything by 3 to the x. Minus 2 over 3 to the x. The limit, limit x approaches to infinity. Now I can simplify these and say what is left is limit 1 over 1 minus 2 divided by 3 to the x as x approaches to infinity. And this could be written as limit 1 divided by 1 minus 2 times 1 divided by 3 to the x is the same as 1/3 to the x. Ignore this 2 right up front here. This is the same as 1/3 to the power x. And now as x approaches to infinity, what we get is this term approaches to 0 because the base is between 0 and 1. 2 times 0 is 0, so you get 1 divided by 1 minus 0, which is 1. This, if you forget the limits, just draw a graph and say, okay, the base is greater than 1, you have an increasing function. If the base is smaller than 1, like 1/2 to the power x or 1/3 to the power x, what you get is a decreasing function. And then you can discuss the behavior. As x approaches to infinity, y value is approaching to 0. That's what the y value. Okay, now we get to the important part, the derivative of the exponential function. So before I give you the formula, I want to go through this idea how to calculate the derivative for the exponential. How do they came up with this? Is normally every time you see a new function, if you want to calculate the derivative, you have to go back to the original definition, the quotient. So the derivative was the limit of f of x plus h minus f of x divided by h as h approaches to 0. If the function is given as b to the power x, then the quotient would be f of x plus h would be b to the power x plus h minus f of x is b to the power x divided by h. H approaches to 0. And now I can rewrite b to the power x plus h as b to the power x times b to the power h by one of those properties that we had for the exponentials as h approaches to 0. And what you see in common is b to the x, so I can factor that out. And it's independent of the limit because the limit is for h. So I can basically write outside limit h approaches to 0, b to the h minus 1 times h. So now the question is, what is this limit? Because if I can answer this limit, then I've answered the question. This is the important part. Can I answer what is this limit? If I can answer that, then I have the derivative. This is if you pick different bases, you will get different results. For example, if you pick the base to be 2, this limit may be a decimal number. If you pick the base to be 10, you'll get a different decimal number. But those decimals could be calculated through calculator more and more precisely. What I'm going to mention is to say, okay, let's call this b to the x times some number, star. There is a specific case that this star is the result of this limit. There's a specific case that we can answer. And that is what we call it the number e. Which is, oh here, I already wrote this number. E is 2.718, it's like a pi. What is the property of this number? Is that this limit is simply 1. So if I know this limit is 1, that means if you pick the base to be e, the result of this limit would be simply 1. Then I can answer the question that what is the derivative of e to the x? Because then the derivative of e to the x would be e to the x times the limit, which is simply 1, which gives me e to the x. Right? This was calculating the derivative. So if I pick the base to be e, I can answer this derivative and say the derivative is simply e to the x. For the other bases, we still don't know the derivative. Hopefully we'll discuss it later on, but at the moment I can answer this fact that if I pick the base to be e, then I know this limit. I know the limit is simply 1. So you will have e to the x times 1, which is e to the x. So the derivative of e to the x would be e to the x. And what I can answer is, what is the integral of e to the x? Remember, the integral is basically going backward in the derivative. So if I give you that, can you tell me what is the original function? It's the same as e to the x. E to the x has this property, the derivative and the integration of it is the same function. This is a really nice function. And how does it look like? E to the x function. An increasing function since the base is a positive number greater than 1. The base in this case is 2.71828. I think you can continue this. There may be more in the book, 285 something. Yeah, 4 or 5, I think, after this. So on. It's a transcendent number. It doesn't end. There is no repetition. You'll never find the loop into these numbers. It will go on forever. So if you see this e to the power x and they ask you for the derivative is simply e to the x. What would be the integral of e to the x? It would be e to the x plus some constant c, whatever that constant is. And implication of chain rule, we already know the chain rule. So if you have e to the power u and they ask you to calculate the derivative of e to the u, the derivative of e to the u would be e to the u multiplied by the derivative of the exponent. The variable here is whatever the exponent. This is the chain rule. Would be du divided by dx. Right, you take the derivative of the outside function. The outside function in this case is the exponential, which stays the same, multiplied by the derivative of the inside, which is the exponent, e to the u. Here is a bunch of examples. So let's find the derivative of these functions. D over dx of e to the 3x squared. This is the exponent. This is the same as u. So what would be the derivative? E to the 3x squared multiplied by 3x squared derivative, which is e to the 3x squared multiplied by 6x. And that's it. Normally, I would prefer to write the 6x in the front. This way you do not mix up the exponents and the coefficients. So this is the derivative of e to the 3x squared. How about the derivative of e to the tangent? It would be e to the tangent multiplied by the tangent x derivative. And this would be derivative of tangent x squared is secant squared x multiplied by the e to the tangent is still there. Derivative of e to the x is e to the x multiplied by the exponent derivative. But what is the x derivative? It's simply 1. It's the same as saying e to the x derivative is e to the x. You can always imply chain rule on any type of function. How about this one? Derivative of x e to the x. There's a product here. So you should use product rule. All those properties that we learned early on still apply here. So it will be derivative of x times e to the x plus x times derivative of e to the x. X derivative is 1, 1 times e to the x, plus x times derivative of e to the x is still e to the x. So what you get is e to the x plus x e to the x, which you can factor out e to the x and say this is 1 plus x. How about the integral? What is the integral of 3 e to the x? 3 is a coefficient constant. I can write that side. What is the integral of e to the x? We learned that the derivative of e to the x is e to the x, so the integral of it would be still e to the x plus some constant. Nothing complicated about this. The simplest function to take the integral and derivative. How about the integral of x e to the x squared? So now here you require substitution because it doesn't look that simple anymore. It's not e to the x to take the derivative. So what do is I'll pick x squared, I'll pick u to be x squared. du over dx would be 2x. So du divided by 2x would be dx. So here I can write this integral as x times e to the power u, multiply by, instead of dx, I'll write du divided by 2x. These x's will cancel out. You'll have 1/2 integral of e to the u du, which is equal to 1/2 e to the u plus some constant c. The integral of e to the u is e to the u. And therefore 1/2 e to the x squared plus c. Antiderivative. Again, everything that we've learned so far, it holds. You can take the derivative, you can integrate, you can use substitution. But the only thing that we learned is that the derivative of e to the x is e to the x, the integration of e to the x is e to the x as well. Here, for example, you can find the tangent line. You can find the chain rule, what is it? The concavity, everything is still the same. So here in this case, I picked this implicit differentiation required here. To take the derivative, we need to find out what is dy over dx. That gives us the slope. Then we have a point. Okay, so we're looking for the tangent line. So to find dy over dx, say x e to the y plus y e to the x minus 1 derivative equals 0 derivative. Derivative of left side would be x derivative times e to the y. You need product rule plus x e to the y derivative, use parentheses, plus y derivative e to the x plus y e to the x derivative. Minus 1 derivative is 0, the other side is 0. Okay, derivative of x is 1, e to the y plus x e to the y times derivative of y with respect to x, or y prime, either way you can write it, plus y prime e to the x plus y e to the x derivative is e to the x equals 0. So now I just need to figure out what is y prime. So keep the terms that contain y prime and move everything else to the other side. X e to the y prime plus y prime e to the x equals negative y e to the x minus e to the y. And now factor out the y prime. These are the steps that we have done before. The only Difference is we never did implicit differentiation with exponential function because we didn't know the derivative. Now that we know the derivative for e to the x, we should be able to use the same idea. So the derivative is negative y e to the x minus e to the y divided by x e to the y plus e to the x. So what is the slope? Given the point was given 0 and 1. So I'll replace x with 0, y with 1. Negative 1 e to the 0 minus e to the 1 divided by 0 e to the 1 plus e to the 0. And you can calculate the numerator. E to the 0 is 1. E to the 0 is 1. 0 times this will cancel out. E to the 1 is still e to the 1. So we have negative 1 minus e to the 1 is e. And the denominator is 1. So you get minus 1 minus e. We found the slope. And the point is given 0, 1. So you can say y minus 1 equals the slope, negative 1 minus e times x minus 0. What is this? This is basically the equation of the line. It involves e, but e is a number. E is like pi. It doesn't do anything special. It's just a constant. So, by the way, I didn't mention this, but I think it should be clear. If I ask you, what is f prime? We've talked about this. It's a pi is a constant, derivative is 0. If it's given only e, the derivative is still 0 because e by itself is a number. E to the power x is not a number, it's a variable. E to the power 3, derivative is still 0. E to the power e, derivative is 0. But the moment that I change this to e to the x, this is an exponential function. E by itself is just a number, it's 2.7. But to the power x, derivative would be e to the x. Okay, this is basically it for this section. I hope you try some examples. I cannot go through a million examples, but they will be very similar to what we've learned. You just need to make sure that you take the derivative correctly and the integration correctly. Use these two properties. And in the case of chain rule, you can use that. Okay, so let's stop here. Next time we'll talk about the inverse of exponential function, which is the logarithmic function.